Thank you very much for this invitation. Let's start. I would like to tell you a little bit about our recently announced NQCC testbed and argue this is how we are hoping to enable future innovation. Okay, let me first start saying that we're all here for the roadmap to quantum value. We are all very excited. As we just heard, there is many mature quantum hardware emerging. There is lots of fantastic applications going there. And this is exactly the critical moment. The issue of trust for technology adaptation should panic all of us. Why should panic us? Because if we don't address the critical question of the trust, the appetite of the market will change in the sense that what's going on, what is the real advantage that we can obtain. If we don't address the hype, eventually the investment will trigger around, and they want to figure out where is we really getting the devices that is working, and etc. It could be a barrier for innovation because we need to figure out exactly what are the challenges that are emerging in the field so that we can continue this roadmap to the value. And it's also, I guess everybody here are aware that rushing to the market before having really understand how to benchmark and test and correct this thing, it will be immature because the expectation of what we're trying to offer will not be satisfied by our end user. And of course, we have a very good example of this in the sector of the AI. If we let this thing grow and only later on trying to figure out the issue of the trust, benchmarking, interpretability, will be too late, and then we cannot even apply the regulation. And on the other hand, navigating this quantum trust landscape is also very complicated. Who do you want to trust within this trust system? Do you want to look at the hardware provider that they're coming and say that my device is the best? Do you want to talk about the software provider that are pushing a particular application that they want to go for the trust? Do you want to listen to your academic, which are trying to talk about quantum supremacy? Do you want to go to the regulation that they have their own rules and etc. and national interests? Obviously, you need to also address the question of competition versus collaboration. Can we put everybody together trying to do something yet provide the competition landscape that they need to go? And things goes on and on. Everybody has heard it, but I want to make sure that you're all in the same page. This is complicated landscape. So we need to have a very clear metrics that is allowing us to go through this path. It should be independent, and I'm going to spend most of my talk talking about it. And more important, it should be for empowering our end user, so they know exactly what they're talking about, how to go, and how to make their decision making in terms of what is best for their business. Well, standardization, we know is very complicated for any technology, and trust me, for quantum it's going to become even more complicated, but yet we need to have a uniform framework that allows us to innovate in this space. So why this is such a big deal? We have done it in the classical world. We have plenty of the field. This is not from the scratch we want to invent testing, but we have model checking, hardware testing, software testing, statistical analysis, formal methods, certification, and et cetera, et cetera. So, if you talk to the classical expert, they say, well, just pick it up and try to apply it. The point is, we can talk about it at length, but the issue is that in the classical sector, when we're talking about the trust, it always comes from the fact that it's about security vulnerability and or error that a user will run on this thing. To some extent, I'm exaggerating. But the point is classical devices have a fantastic fault-tolerant system. So this issue of the trust that we are dealing in the classical world, most of this technique, are not because of built-in fault that somebody need to deal with. So it's more at the different level of abstraction. That's why I kind of briefly argue that it doesn't work. If you look at the model checking, which is fantastic, we have tons of Turing Award for it. Because of exponential size of quantum system, you cannot just pick it up off the shelf and apply it. Now I'm going to do quantum model checking. Hardware, the point is that we don't even know the noise of these devices when we go to the 1000 qubits. So how we want for a system that is not classically simulatable to do the hardware testing against the classical performance that we want to have. Statistical analysis, our quantum programming languages will have unnatural quantum control that doesn't make. So essentially what I'm saying, model checking, different underlying logic, etc., is that it is complicated. Okay, don't think that, you know, application hardware, off we go. So we just need to pick up what we have been doing for HPC, and now we roll it over and we do it for quantum. No, it's not going to work. Okay, trust me, I've been spending the last 20 years of my life trying to do that. So quantum trust challenge. If I want to have one message you leave this room is that because what makes quantum not classical, its verification is also not classical. It's all coming from the fact that we have a device that we are waiting for it to be not classically simulatable. So what are we going to do? How are we going to do the testing for it? How we want to do it scalable? How do we want to do it efficient? Is it going to be like fault tolerance that we build a device and we need to have another 1 million qubit to sit on top of it to answer the question of the trust? And this issue of the trust and verification is both for the NISQ device, emerging device, and fault tolerant device. We still need to verify about it. So in the beautiful paper of Dorita Haranov and Umesh Vazirani, they put it a bit more formalized as a foundational question, that if quantum computer is capable to solve a problem efficiently, to provide quantum supremacy, give a quantum advantage, can quantum computer also efficiently convince user, the verifier, that has done so? You know, all of you know that this is a dilemma that we have. It's such a big problem that Scott Aronson in 2007 dedicated $25 of his own pocket money for the Scott Challenge, big challenge, in a very complexity theory language. That he said that does quantum computer, the class of quantum computation BQP, can admit a classical verifier? So this is, if you wish, really back to the same question of falsifiability of quantum mechanics. Can we use our classical devices to say that, yes, this device is working what it's supposed to do? And of course, everybody thought, you know, back in 2007, this is an easy problem. It's just a matter of a bunch of other complex classes come together. But Scott himself hasn't solved it yet. And only a few months ago at Q2B Silicon Valley, he again raised the same problem. So maybe we need to put a bit more money on this particular problem to encourage people doing it. But Scott was mentioning, and I come back to this beautiful figure, that right now, one of the biggest challenges in our field to find something that is efficiently verifiable, is useful, is doing something that somebody wants from industry, and at the same time is truly quantum advantage. And that big question is something we need to solve in order to reach the quantum value, really. So I would even argue, before completely convince you that why you need to listen for the rest of my talk, that I would argue even Richard Feynman in '81 really noticed that this is a big problem. When he said quantum computer isn't classical, damn it, if you want to make a verification of it, you'd better make it quantum mechanical. And that's a hard problem. People thought he was talking about quantum simulation, and they went and built it and get the Nobel Prize, but it's really, building quantum simulator is not that difficult. Testing that this device is really doing what it's supposed to do is really difficult problem. Okay, so are we doomed? What are we going to do about all this? Well, here we are. NQCC is coming to save us all. The point is, I want to share with you in the remaining part of my time so that, who should do this and how should we do it? So give a flavor of it in the next 10 minutes that how we can go it. So obviously, I hope by now you agree that this question of verification, testing, benchmarking, it should be in some sort of independent organization. So our method is at NQCC, with the support of experts from Quantum Software Lab at University of Edinburgh that we have launched, to offer an independent test authority roadmap that, of course, need to still be very collaborative to understand what it is. And I will talk a little bit about what this test bed looks like. And also, hopefully, if I get the chance, I also want to essentially saying that given that this problem is such a complicated problem, we should build towards a zero trust model. In the classical cybersecurity, zero trust model has been applied for many, many sectors. But what we are able to show, and I will again pitch it very quickly, that we can mimic the noise and deviation and the maliciousness of these devices like a cybersecurity attack, and use the powerful technique of cryptography to give us rigorous, efficient, scalable verification. So these are the two things you need to remember from the talk. So NQCC, for those of you who don't know what it is a national lab in UK, which is a collaborative program by EPSRC and SDFC. And The goal of NQCC is sitting between academic and industry, trying to adjust and address the challenge of scaling quantum computing. That's why they have its in-house progress as well as collaborative and acquisition of the various platforms that I'll talk in a second about it. They're trying to build their own full stack architecture for hardware, software, access in the cloud. What I'm going to focus more on the scalability regarding benchmarking, verification, and testing. And of course, we have a very, very active end user program, similar to what we heard about HQI, that, the Spark program is already bringing various end users to work together. But today, we're going to focus on the verification. So the testbed that was just announced, and we acquired 7 different platforms. The idea of this platform and all the progress, it's going to be all the different Lego pieces, if you want. Silicon qubit, photonic qubit, superconducting qubit, ion trap qubit, cold atom qubit. And these are national, international platform. And the idea is to help both with the in-house progress as well as to become the system of what does it mean that somebody come and build a system at NQCC and allowing us to run this test bed that we want to work on that. So in particular, this is the program that is going through, the first phase is deployment of the partner to setting up these devices from scratch build at NQCC or delivering the build-up system. And the exciting part that I'm going to more talk about once the delivery is done is about the whole procedure of benchmarking, verification, assurance, and access to the ecosystem to how to work with this thing. So we launch. We are right at the beginning of the project, but it's going to have, a few more years before we are able to go through this roadmap that I was telling you that, how we're building this trust. Okay, the spectrum of various techniques. Now let's come to the fun part. So there is so many different things that we can do. There is so many questions that you can ask. Whether you look at just the quantum advantage benchmarking, when you want to ask, have we achieved the place that we're doing something that is classically not simulatable? Are we going there? And where we are reaching there? Looking at the noise, device benchmarking, randomized benchmarking, various sort of technique about based on the qubit size, gate size, all the way to the application size. Then mitigation, how do we do while we don't have yet fault-tolerant error correction, how do we do error mitigation, how this thing goes. But ultimately, what we want to do also, we want to have very formal verification. No matter what the device is, how can we make answer to the big question of, is this device, which is popping bunch of number, are good for me? Can I go and build my discovery of new drug and various material, knowing that these data are not bunch of random noise coming from my device, they are actually the computation. So in some recent work, and many such review exist, you can look at this zoo of the various techniques that exist. Some of them are making strong assumptions, some of them has weak assumptions, some of them give you a lot of information about the device, some of them give you less. And I think the whole point is that for a long period during this procedure, we need to look at the unique device figure of merit, tailor-making our verification to this particular one, application-driven, and knowing the fact that one size doesn't fit it all, and it's going to drive us nuts, obviously, to doing all this matchmaking. So while this seems to be the case for the next few years, I want to go back to the very original question that I mentioned, is that can we do a little bit better rather than this soup of everybody picking up their own method and applying it things? And can we really go back to this original question, the zero trust verification protocol, which is my cup of tea, because we eventually want to be able to do that, picking up this black box, interact with it, run my problem, and me being the classical verifier, being able to say something, yes, this computation is correct, or no, it's not correct. So that's the Scott Aronson challenge question that I was mentioning before, to be able to have a certifier of the correctness of the device. And in some, I wish this was an academic talk so I can give you all the last 2 decades of research that has gone to this particular question with the hundreds of different researchers contributing, but I'm going to highlight the latest result that we have been doing in collaboration with CNRS and Quandela and INRIA. And we I'm calling zero star trust quantum computation verification, that we have shown indeed a classical verifier which have access to a little, tiny little bit quantum computer, which is only able to do a single rotation gate. So this is like a minimal amount of trust you can consider. With that, we can bootstrap this little tiny device of quantum to indeed to do scalable verification on everything that you ever dreamed to. So I want to a little bit showcasing you this technology, because it's not right away available so you can plug it to everything. It is a roadmap, but that's the vision that at least I have, that we can make sure that we have this zero trust technique when we want to really talk about quantum computation. So, still you can go and claim a Scott result, because, we only won after this $5 from the whole point, because we're still making some assumption about the single qubit. Purely solving this classically is a beautiful open problem. Okay, here's the protocol, just to show that like it exists, is fit to one slide, so you can really actually doing it. The idea of it is actually very, very simple idea. You have these devices, you're running many, many, many computation on top of them, like a random quantum circuit, etc., benchmarking that we always do. Some of them are tests, some of them actual computation. Those gray are my computation that I have no clue what is the size of it. It's a 1,000 qubit machine that I don't know even what it means to have 0, 1 out of it. But those green, red, colorful ones are designed in such a way that these are deterministic. I know exactly what the computation needs to be. And that's the simple idea that actually exists for the classical hardware testing when you want to do, for example, high-performance computing. So the idea of, the underlying technology is that, okay, you run your target computation, you're running your test computation. For the test computation, you know exactly what the results are. For the actual computation, you don't know. So where's the magic? The magic that I'm not showing is that you're making sure that they are obfuscated. So that's where the crypto technique of zero trust comes. So the device, nobody, whether you are the noisy device, whether you're the provider, etc., you don't know when is the test, when is the computation. The moment you put it in that technique, that's when we are able, by just looking at the test, and make a claim regarding the actual computation. This obfuscation that the device, the noise, the provider cannot distinguish whether right now I'm doing a test or right now I'm doing computation, makes the answer to this scalability possible. We actually implemented it as part of the Quantum Communication Simulation Hub in UK with the Ion Trap group of Oxford. We indeed implemented this with the Ion Trap group to show that this is applicable in place. And in fact, we have also extended it in a recent work that hopefully soon will be archived, that this can build a very sophisticated heuristic-free benchmarking. Is at the end of the day, I started my talk, how do we benchmark? How do we answer the question of what should I do? You want to eventually, in the years to come, to have a noise model agnostic, hardware agnostic, algorithmic agnostic, predictive, certifiable benchmarking that is really allowing you to say something about capacity of your machine. And the technique that I show you can be extended, but there is a price. And this is the message for our hardware partner, that you cannot build your hardware as you wish and then put all the effort on us, the software people, to do the verification. This is a co-development. The same way that for fault tolerant, right now we are influencing the way the hardware should be designed to enable fault tolerance. This is the moment, and that's one of the important parts of the testbed, that we also need to influence the way the hardware is built to allow us to put this technique on board. And what do we need? You need to have mid-circuit measurement. That's the good news, because you need that for fault tolerance as well. You need to make sure every qubit is measurable, at least with our technique. Maybe there's other technique to provide that. But more importantly, the issue of creating, remember I said that our technique is based on the single qubit being trusted and able, and that we do bootstrapping. So you need in your hardware, if you cannot link it with the photonic to the external part, you need to have an isolated single qubit zone that I need to use that as the basis of my trust and bootstrap and trying to say something about the rest of the computation. And that's something that some of the hardware already doing it. Again, in the view for fault tolerant, we are exploring some project with Continuum, which exactly has these bits and pieces in order to see what is the best architecture that by design enabling us to do the verification. So just to wrap up, what do we want to do next? Can we really do this platform, like excited little kids? We have now all these different platforms, and we want to apply this technique to understand are they applicable, what is missing from the theory point of view, how we can adapt them better to really provide this verification. And of course, going back to the original question, that is it again, we can find using this technique, answering the efficient verifiability advantage, as well as making it something for the NISKI devices. So just to finish, the testbed is an exploratory journey. You know, we have several already platform, but it is exactly like all the call that you sing from the different national program. It is open. We need to do this game together, and we need to help each other to navigate the hype. And we are essentially in the next few years, I think we are going to be a constructive hackers to make sure that we can design a future devices that is scalable, verifiable, and fault tolerant. Thank you very much.
Thank you, Elham. A couple of questions. So, and I'm going to paraphrase a couple of these together. So, as you continue to expand the NQCC, how do you decide which hardware devices maybe to purchase or lease to have on site?
I will let the executive director of NQCC to do that, so I can do my science. So I think there will you know, navigating that question is also very, very, very complicated. I think, you know, as we heard from Sabrina, is like there's lots of factors. You know, what works for the UK ecosystem, what works for the national, what works for the international. So essentially, I'm blah-blahing. I don't know how to do that. And I think it's part of the whole problem. And I don't think even the fact that, oh, we run our verification, you pass it, so that's the good reason to go. And the reason is that maybe a device that is very mature today is not going to be the mature, scalable devices of future. So we need to be careful. That's why so far in the UK national program for the last 10 years, we have not picked up the winner. And we're still trying to see for how far we can resist the politician push to pick up the winner, and yet trying to make sure we are innovating in all the platform.
Okay, related to that, let's say a commercial hardware developer would like to have their device tested, but want to keep it confidential at first. How do you handle potential, you know, proprietary or confidential information?
I think that's also a very, very interesting question, and that's again why makes us excited about testbed, because we need to address all of them. Right now, this matter of the 7 qubit being the 7 platform that being the one that we are working with is not just matter of those platforms, it's just also understanding what it works, because UK is trying, and NQCC trying to be, if you like, the professional customer. We are the customer at the same time as the provider of the trust. So we need to work with our partner in the next few years to see what works for them, and that would be a lesson. You know, I think some of this benchmarking testing, especially the way that I presented, doesn't need to know all the details, and yet we need to have some sort of access. So it's not white box access, it's not black box access, it's some sort of gray box access that we need to develop to be able to rule out this verification and testing.